Welcome to this video on Hilbert space, the mathematical architecture of quantum reality. We will cover the theory, derivation, and physical insight behind this crucial concept. In classical physics, we describe space using simple coordinates. However, in the quantum world, a particle is a collection of possibilities. To describe this, we must move from a space of positions to a space of functions. This is why we need Hilbert space. We begin with part 1, the axioms, focusing on building the mathematical stage for quantum mechanics. The first rule of Hilbert space is linearity. If we have two quantum states, called psi and phi, any combination of them is also a valid state. This is the mathematical root of the superposition principle. Unlike classical vectors, Hilbert space uses complex numbers. This allows quantum states to have a phase, which is essential for phenomena like interference, where waves can reinforce or destroy one another. Next, we move to part 2, the inner product, which defines the, quote, overlap of states. We represent states using Kipnis and Bras. A ket is a vertical vector representing the state, while a bra is its dual vector. Together, they form the inner product, which is a single complex number representing the similarity between two states. The inner product is conjugate symmetric. If you flip the order of the states phi and psi, the result becomes the complex conjugate. This ensures the math remains consistent when calculating physical probabilities. When acting on a sum of states, the inner product distributes across the terms. This mathematical property allows us to calculate how a complex superposition interacts with a single measurement state. The inner product of a state with itself must always be a positive real number, or zero. This value represents the square of the length of the state vector. In physics, if this length is 0, the particle does not exist. Part 3 asks, why Hilbert? This involves understanding completeness and infinite dimensions. In simple terms, completeness means there are no holes in our mathematical space. If we add up an infinite number of small quantum ripples, the final result must still be a valid quantum state within our Hilbert space. We use the term Cauchy sequence to describe vectors that get closer and closer together. A Hilbert space guarantees that the limit of such a sequence is always found within the space itself. This is vital for solving the Schrodinger equation. Physically, the integral of the square of the wave function must be finite. This ensures that the total probability of finding a particle is finite. If a function satisfies this, it belongs to the Hilbert space called L2. Part 4 covers the basis, which means expanding states into simple parts. Just like any point in 3 dimensions can be described using x, y, and z, any quantum state can be built using a set of basic building blocks called basis vectors. The coefficients tell us how much of each building block is present. Basis vectors must be perpendicular to each other and have a length of 1. This is called orthonormality. It ensures that the building blocks of our space are distinct and properly scaled. Hilbert spaces can have a finite or infinite number of dimensions. For spin, we only need 2 dimensions. But to describe the position of a particle, we need an infinite number of dimensions to account for all possible wave shapes. When we represent a state using energy levels, we often use a sum. However, when we represent a state in terms of position, we use an integral. Both are valid ways to describe a vector in Hilbert space. The completeness relation states that summing up all the project operators for a basis gives the identity operator. This is the mathematical proof that our set of basis vectors covers every single corner of the Hilbert space. Finally, we explore part 5, physical reality, connecting vectors to experiments. In Hilbert space, the identity of a quantum state is defined by the direction of its vector. We don't care about the absolute length as long as it is normalized to 1. Moving the vector rotates the particle into a different state of being. The most important link between Hilbert space and reality is the Born rule. It tells us that the overlap between two vectors, squared, gives the probability of finding a particle in one state if it started in another. If states are nouns, operators are verbs. They act on vectors in Hilbert space to change them or extract information. Every measurement we perform in a lab corresponds to an operator acting in this abstract space. To summarize, Hilbert space is a complex vector space with an inner product, and it is complete, holding all quantum wave functions. Always remember the distinct parts of Dirac notation. The ket represents the state, the bra allows us to perform measurements, and the combination results in a number we can use to predict the outcome of experiments. Thank you for watching this video. For more information, please visit the contact details on the screen.